Buenas tardes, bienvenidos al Seminario Fronteras de la Energía, organizado por el Instituto de Energías Renovables de la UNAM. En esta ocasión tenemos el gusto de presentar a la profesora Jenny Nelson, que es miembro de la Royal Society. Como dato, la Royal Society, fundada en 1662, es la sociedad científica más antigua del mundo y dentro de sus miembros están algunos de los científicos más importantes de la historia de la humanidad, por ejemplo, Albert Einstein y Isaac Newton. Y como cortesía a nuestra invitada, voy a cambiar al idioma inglés y voy a hacer una pequeña eh, reseña de la trayectoria académica de la profesora Nelson. Professor Jenny Nelson is a Royal Society Research Professor at the Imperial College of London, where she researches novel materials for solar energy conversion. Her current research is focused on understanding the structural property relationships in molecular and hybrid semiconductor materials and how these relationships influence the mechanisms of solar energy conversion. She also works on the role of renewable energy technologies in mitigating climate change. She holds several awards, including the 2016 Institute of Physics Faraday Medal and the 2023 IEE PBSC Cherry Award, and was elected as a Fellow of the Royal Society in 2014. Professor Nelson, thank you very much for accepting the invitation to participate in this seminar. You may start. You be my guest.
Okay, shall I begin?
Yes,
Yeah.
please.
Yeah.
Thank you.
Okay. So thank you, Filiberto, for the invitation to give a talk to the Institute of Renewable Energy at UNAM. And I've never visited, actually, I've never been in Mexico, but this is my first time to visit Mexico virtually, so it's still an honor. And I'm going to talk to you about some of our research, which is about using molecular electronic materials for energy conversion, mainly for solar energy conversion, and a little bit about storage. So the context of this, the context of my talk and of my research is that we're living in a planet which is heating up quite badly. And these are data that you can collect from the internet, but they simply show that over these recent years, and I mean this is the period of time over which I have been active in research. The temperature of the planet has been changing significantly, and particularly over the last couple of years, these have been hotter than it's ever been before. This is a very serious problem that threatens our planet, our ecosystems, humanity, and everything else. And if we want to constrain the climate, the global warming to a reasonable level, for example, if we could constrain the temperature rise to well below 2 degrees centigrade, then we would have to make some changes in behavior, and a part of this concerns energy generation. So at the moment, electricity generation accounts for about 25% of the planet's greenhouse gas emissions. And if we want to eliminate that, if we want to eliminate emissions generally, there are really two things that we need to do. So one is we need to meet more of our primary energy needs from electricity, rather than, for example, from heat from burning fossil fuels or whatever. And that's what's represented by the first graph. So these gray lines represent the results of different scenarios that are run with different integrated assessment models, with the target that the global temperature should not rise more than 1.5 degrees. And the green line is a kind of median. And all of these scenarios, although they differ, they're all telling us the same thing. We need to produce more of our energy from electricity. And the reason for that is that electricity can be decarbonized, whereas other things like fossil fuels for propulsion, petrol, diesel, whatever, cannot be so easily decarbonized. And the second point is that most of this electricity is going to come from wind and solar generation. So these are two things that are fairly clear. And so the point is that solar energy and solar electricity are going to be important in a low carbon future. So to look at solar energy, so we have the sun. It provides us with energy in the form of radiation. We receive it as photons, and the energy of the photon is associated with its color. And when we receive these packets of energy, then we can absorb them in materials and we can do different types of things with them. And what I will mainly be talking about, and what is mainly the subject of my research, is solar photovoltaic energy generation. When the photon is absorbed in a semiconductor, which is connected through asymmetric contacts to an external circuit, and it then produces electron hole pairs. They produce a current that flows through an external circuit and is able to do electrical work. And it's anticipated that after 2050, or maybe even before, solar photovoltaic power will become the largest single source of electricity. As well as that, solar power can be used to generate heat. That's something which has been going on for a while, and it's something which is now expected to grow quite rapidly. And as well, solar power can generate chemical, can be the source of energy for chemical fuels. So of course, this has been happening for many thousands or tens of thousands of years through photosynthesis, but the same principles can be used to generate fuels in a modern way, either with artificial photosynthesis or by combining low carbon electricity like solar PV together with electrolysis. So we see that solar could be an important source both of electricity, of heat, and of chemical potential energy, all of which we would need. So when we think about solar PV generation, we normally think about providing electricity to meet the usual electrical demands. But as solar power becomes more available and cheaper, as it has been doing over the last years, it has more applications. And amongst these, there can be the integration of solar photovoltaic generation into buildings so that you're generating power in the same place where it's needed. It can be integrated with transport by providing the power for electric vehicles, integrated with agriculture. So the field of agrivoltaics is something relatively new, but which is now growing very strongly. And we may also combine solar electricity with solar heat, with solar desalination, and with solar fuel generation. So all of these different ways are ways in which the sort of solar power can be integrated with different sources of electricity. And a point to make here really is that with this wide variety of applications, that leads to quite some variety in the requirements, both of the materials and of whatever device or technology they're integrated within. So although silicon solar panels are already quite mature, they're quite cheap and quite widely used, there's still any number of applications for other types of solar technology. It's still something which is worthwhile studying and worthwhile doing research in, particularly for our next generation of scientists. So I'm going to talk about a particular class of semiconductor materials, which we call molecular electronic materials. And so unlike something like silicon or gallium arsenide, where you have a crystalline inorganic material, which is a semiconductor, we have materials that are based on carbon and hydrogen. So they're based on light elements, but they're based on carbon, which is hybridized in its sp2 configuration. And what that basically means is that our structure, so a molecule, a macromolecule, made up from a backbone of carbon atoms in this sp2 configuration, is able to share these what we call the pi electron density amongst the different carbon atoms, and that gives the material the properties of a semiconductor. It provides this sort of cloud of electrons which can be relatively easily disturbed, so they can move through the material, they can give us electronic transport, and they also give rise to optical transitions which have energy in the visible. So it allows it to absorb and emit light like another semiconductor, and it also allows them to conduct electricity. So if we just have, so what I have in the diagram here, this is a molecular dynamics snapshot of the inside of a film which is made from a polymer that we call polythiophene. And if we were to excite this polythiophene by shining light on it, we could, with the photon, we could excite an electron from the lower energy state that we normally call the highest occupied molecular orbital to a higher energy state, which we would call the lowest unoccupied molecular orbital. So these are equivalent to valence band, conduction band with conventional semiconductors. And so we would have created an excited state. But in a single material, it's unlikely that we could then separate the electron and hole because they're quite strongly bound together. And that's because this material has quite a low dielectric constant. And with a low dielectric constant, there's little electron density available to screen the charges from one another. So they hang together and then eventually they recombine and they fall back to ground. And so although we absorbed a photon, probably what will then happen is that we lose that excitation, maybe by emitting a photon. And that's not useful for solar photovoltaic energy conversion. So what we do to solve this problem is we introduce another material. So we then have two semiconductors, two organic semiconductors, and they would differ in their energetics. So if we look at them as semiconductors, they form a kind of a type 2 heterojunction, where in one material, the electron will be stabilized, and in the other material, the hole would be stabilized. And this has the effect of changing the distribution of states that are available. So now we not only have a ground state and an excited state, but we also have configurations where we could have an electron on one side and the hole on the other side of this heterojunction. And we usually call that a charge transfer state. So it's a state that's stabilized at the interface. And then eventually, when the electron and hole escape from each other, we have what we call a charge-separated state. And that's actually what we want, because we want to be able to carry the electrons away so they can contribute to an external circuit. And so what happens now if we come in with a photon? So we will excite an electron from ground state to an excited state. And then rather than that electron falling back down again, it's now able to take part in charge transfer. And so the electron could be transferred from one material to the other. So for example, if the photon was absorbed in this polythiophene here, then from the excited state, the electron could transfer to the other material, which in this case is a fullerene. And then we would have hole here and electron here, and we would have a charge transfer complex sitting across the heterojunction. So this state is more stable. And then if we provide, if we give it more time, it can then separate further so that the electron and hole escape from the heterojunction, and then they're available to travel through the external circuit. And so these are the things we would like to happen. And of course, in real life, nothing is completely efficient. So we may also have reverse processes going on. So we want the green things to happen. We don't really want the red things to happen, but they may happen anyway. So this is the kind of the principle. And this is a principle that's been known for some time. The first invention really was almost 40 years ago by Qing Tang, who was working in Kodak at the time. And then more recently than that, the concept was developed. So why would we bother trying to make solar cells from materials like these? Well, there's a number of reasons. And one of the sort of traditional reasons is that these molecular materials can be processed relatively easily with relatively low cost and relatively low energy input, because they could be processed by solution, and as such you could coat them into large area devices relatively easily, and then produce sort of large area materials. We also have some control over the properties of those materials by changing the processing. So that's kind of the sort of the traditional reason. There's another reason that's popular nowadays, and this is that these materials are interesting in their modularity. So if we want a particular chemical structure, we can make it up from a lot of different, by combining different motifs together. And actually, if you understand the relationship between these chemical groups and the properties of the material that you would finally make, then you have the opportunity to kind of design materials that may have particular properties. So we may design them to absorb light at a particular wavelength, or to have certain electronic properties, or to have different mechanical properties or whatever. And they've become quite popular as kind of materials with which to study molecular design, inverse design, and the sort of the combination of chemistry with machine learning. In a more practical sense, the materials are interesting because you can prepare them in different formats. You can make relatively conformal shapes. You can make flexible structures. And we also have control over the optical properties, which mean that uniquely with these materials, we can prepare films that are optically transparent, because we shift the absorption band into the near infrared, so the material can harvest and use near infrared light, but then allow visible light to pass, and then you could use them in windows, for example. So there's some of these different properties. Another one at a more scientific level, the systems are actually quite interesting, because the whole process that's going on in terms of harvesting a photon and then having these steps of successive steps in charge separation to finally generate an electrochemical potential, it's closely analogous to what happens in the first stages of photosynthesis. Except in that case, you're generating chemical potential energy rather than electrochemical potential. But there's a nice sort of scientific analogy, which is interesting to study. So we have all these reasons, and then one of the most compelling reasons is actually that recently the performance of solar cells made from molecular materials has been increasing quite rapidly. So this is a typical device structure where we have two electrodes. They need to be electronically different in order to drive a photocurrent. Typically, we would have two layers of different work functions, and that would provide a direction for photocurrent to be generated. And in between, we have our semiconductor active layer that contains a mixture of two different organic semiconductors. And that concept hasn't really changed over the last 20 years. So if we go back to around about the time when I started working in this area, the best efficiency was about 2%. We were very excited when it exceeded 2%. And then over the years that followed since then, as scientists began to understand what was needed from the materials, with the introduction of different materials, new polymers, efficiency went up and up and up, got past 10%, which is a place that was quite surprising at the time. And then traditionally, the acceptor was always made from a fullerene. And then about 5 or 6 years ago, a breakthrough was made where alternatives to fullerenes were found that were able to work well as the second component, as the acceptor component in the heterojunction. And then once that happened, the efficiency shot up. You can see it happening here. These are the new acceptors, and the most recent results are more than 20%. In fact, I have seen a 21% already reported. So the efficiency has been sort of increasing and increasing despite expectations. I certainly didn't expect to be exceeding 20%, and it's quite exciting to see this happen. And so then the question is, how far can we go? Can we get further than this? Can we ultimately compete with silicon? And if not, why not? So those are going to be some of the questions that I look at today. So to sort of set the context of our molecular materials alongside other photovoltaic materials, I'm going to use these data. They come from a publication by somebody called Osbel Almora. He has published, I think, now four or five editions of this paper. This is a link to the most recent one last year. And what he has collected here are recent reports of power conversion efficiency for some different types of solar cell materials. And everything that's highlighted is a relatively recent report. Then the shapes in the background are older reports. And here we have the pink ones are the organic systems. That's what I'm working with. The yellow ones are perovskites. If you work on solar cells, you definitely know about lead halide perovskites. And then the blue ones are compound inorganic semiconductors like kesterites. And in all cases, you see that there's quite a range of band gaps, and that's possible because with each of these families of materials, there is a variety of chemistries, a variety of different components that could control the band gap. And the blue line here, this is what we call the Schottky-Queisser limit to efficiency. So it's a kind of thermodynamic limit to the efficiency of a solar cell. And so nothing is at the limit. The thing which is closest to the limit is gallium arsenide. If you worked on solar cells, then you will probably know gallium arsenide is number one. But of course, gallium arsenide is very expensive, and it won't really, it's not at the moment looking likely that gallium arsenide will scale. So when we compare our molecular electronic materials with others, we see that in terms of efficiency, they don't perform quite as well, although they have been improving. And when we look in detail at the different components of the efficiency, the short circuit current density is not bad. It's kind of following the thermodynamic limit just as well as the other materials do. But in terms of open circuit voltage, it's kind of underperforming. The open circuit voltage generated is not quite as good as it ought to be. And the fill factor, this is kind of a measure almost of how well it collects the charge carriers that are generated. It's not performing quite as well as it could. So these are two things which present a challenge that we would like to improve. So what I will talk about next, I'm going to talk about how we quantify the performance of our, in this case, molecular solar cell relative to the thermodynamic limit, and look at how the molecular solar cells perform and what the reasons are, what would be the ways in which we could improve performance. And then I will go on to talk about some other ways of using organic semiconductors. So I'm going to start with a little bit of physics. And I mentioned in the previous 2 slides ago, I think that there was a thermodynamic limit to the efficiency of solar energy conversion. And the maximum efficiency is about 31 to 33%. And that's what you can achieve if you have a single junction operating in what we call a standard solar sun, a standard solar spectrum. And there's a good reason why that is not. So that basically comes from the fact that the sun is giving you photons of many different energies at once, and you're trying to capture them and use them with a semiconductor that has a particular band gap, a single band gap. And if you make that band gap too small or too high, you won't get a high power conversion efficiency. There's a kind of an optimum where you get the best, and that optimum, it's just about in the near infrared, and it will give you, in theory, a power conversion efficiency of the low 30s, 31 to 33%. Now that's where we would like to get to, and that limiting efficiency also, the physics that underpin that limiting efficiency, that thermodynamic model, also allows us to work out, if we have a real solar cell and it has a particular band gap, we can work out how well it ought to perform. And if we then look at how well it does perform, we can see how far away we are from the limit. And if you're far away from the limit, it's likely to be because there are avoidable losses going on in the material that are not accounted for in the thermodynamic limit. So I'll try to explain what I mean. So when we have a solar cell, normally what we do, we have our semiconductor, our photons of light come in, and they generate charge pairs, and a current is conducted through an external circuit. And we can define the efficiency of generating this current in the external circuit as the external quantum efficiency, or the photocurrent quantum efficiency, and that is really how much current do we get out for every photon that was incident. And so that's something that we can measure. Now, there's another thing that we can do with the solar cell, although we don't normally do it, but it can be done. And that is that we turn off, we don't illuminate it, but instead of illuminating it, we apply an electrical bias. And we apply the electrical bias to drive the current the other way, so that we're pushing electrons and holes into the semiconductor from the contacts. And then when they come in, they recombine. And when they recombine, they will emit. They'll either recombine without light, we call that non-radiative, or they recombine giving out a photon, and we call that radiative recombination. And we can measure this radiative recombination that comes out of the device. We would then recognize it as being electroluminescence. So that's the same as the idea of using a light-emitting diode. You apply an electrical bias, you push current in, and you get light out. So if we measure the electroluminescence and we measure the external quantum efficiency of the same device, these two quantities should be connected to one another. And they're connected through a principle of reciprocity, which basically says that the efficiency of photocurrent generation and the efficiency of light emission are related to one another in the thermodynamic limit. And we can use information from actually either of these measurements to work out. So if we measure the amount of light that our solar cell gives out when we run it as an LED, that will give us a quantity, which is the electroluminescence output, that will allow us to work out how well the device would perform relative to an ideal device with the same band gap. And one of the important quantities then is we can work out the radiative, the voltage that the device would have in the radiative limit. We call that the VOC rad, and we could then compare that with the real voltage. So if we take a simple case, so in the case of Shockley and Queisser, when they considered an ideal solar cell, they make the following assumption. They assume that it has a very well-defined band gap, and that above the band gap, the external quantum efficiency is 1. That means every incident photon gets absorbed and converted into electrical current. And if that's the case, that can only happen if you have no non-radiative recombination. So my squiggly line here, that should not happen. We would only have light being absorbed, and some light would be emitted. This can't be avoided. If you're absorbing light, you must emit it. That's where the reciprocity comes from. But all other loss processes are turned off. And then when we have this configuration, then we get this Shockley-Queisser limit. It's the same that I showed you before. Different band gaps have a different limiting efficiency. Now, if we go to, and that Shockley-Queisser limit would correspond to the voltage the device would deliver would be the same as the one that it gets in the radiative limit. Now, if we go to a real material, like our molecular solar cell, now we have something more complicated rather than simply having a single band gap. So first of all, the absorption edge might be more curved. And we also have this additional state at the interface, the charge transfer state. And so we have absorption and emission that can happen through both of these states. And that leads to a spectrum that's no longer a nice step, but it's quite curved. And when that step is curved, that has the effect of bringing down the maximum voltage that solar cell can deliver. And so our radiative open circuit voltage is less. And then finally, we make a solar cell and we measure it and we see what voltage we get. And normally that voltage will be smaller than the radiative limit. So we've got now a gap between the real voltage that you measure from the solar cell and the one that you expect to have from that solar cell if the material with this EQE spectrum was working in the radiative limit. And the difference between these, it can be quantified in two different ways. We can quantify it as being a gap in voltage between what you should ideally be able to get from that material and what you actually get. We call that the non-radiative voltage loss, but it can also be quantified by a radiative efficiency. So this quantity, eta EL, is telling us how much of the recombination that occurs in this solar cell occurs radiatively. Radiative recombination is good, it can't be avoided, but non-radiative recombination can be, in principle, avoided, and that is a loss pathway that we want to avoid. Okay, so that's the end of the physics for the moment, and now we can look at how materials actually behave. Now, in this graph, I have a lot of different data points, but what I'm showing are the different data points as a function of this quantity that I just defined, the non-radiative voltage loss. So the ideal solar cell would have a zero loss. It would be over here at the right, and would also have an electroluminescence quantum efficiency of 1. And when we look at different materials, we see gallium arsenide, the best material is over here. These are materials with high radiative efficiency. And when we started to do this type of analysis on organic solar cells, they were actually performing quite badly. And they had a rather low, the rather high non-radiative voltage loss and a poor radiative efficiency. This is back in 2015. But by the time we reached over 19%, which was a couple of years ago, that had greatly improved. And in terms of their thermodynamic losses, the organic solar cells were as good as a typical crystalline silicon solar cell, and now they will even be a little bit better than that. So this has been improving these non-radiative losses. However, they're still not competitive with gallium arsenide, and they're still not competitive with the best perovskite solar cells. So what could be the reason for that? Well, now it's worth looking at this recombination process. So I introduced earlier on this interface where charge separation happens. We absorb a photon, maybe in the polymer, and then you have a charge transfer, and you generate this charge transfer state, which then separates, and the electron and hole go off to the external circuit. Now, the process that we want to avoid is when those two charges come back together, and the place that they can do that is at the interface. And so if they come back together at the interface, they can form this state, this charge transfer state, and that charge transfer state is able to decay to ground. And it could decay to ground non-radiatively by giving out vibrational quanta or phonons, or it could decay to ground radiatively by giving out photons. So these two things can happen, and we can actually calculate the rates of these processes if we use some formalisms from physical chemistry. We can calculate a radiative and a non-radiative rate of decay. And we can look at, in fact, how different materials perform. And in this graph here, I've collected some data. They're showing, it's showing the non-radiative voltage loss, and all these blue points are for organic solar cells that come from the literature. You can see that these numbers are relatively high compared, for example, to gallium arsenide or silicon or perovskite. And we would like those numbers to come down. We can see that the numbers do come down for larger bandgap devices, but still they're rather large. And in the work where this was introduced, which is a paper I've cited over here, the argument why these voltage losses were high was all to do with the chemical structure of the materials. So I mentioned that the materials are made from carbon atoms that are linked together through this pi conjugated backbone. And the vibrational modes of these carbon-carbon networks are quite high, and they're quite strongly coupled to the electronic modes. And what this means is that there's a relatively efficient way of dissipating energy, of losing energy in first state to decay to ground. And it was believed, it was proposed that that was the reason why these the voltage losses were so high. So that was something that we then explored in my research group. It was the work of a former student called Mohammed Azuzi. And we did some calculations with quantum chemistry and explored a variety of different structures. And we also developed a thermodynamic model to look at what is the dependence of this non-radiative voltage loss on different properties of the material. So it could be the energy of the state, which is first generated by the light. So that would be the sort of band gap or the first transition energy of the polymer, and then the energy of the charge transfer state, the oscillator strength or the brightness of these states, and then something that we called the reorganization energy, which is a measure of the electron-phonon coupling, how easily the energy can be dissipated. And when we did, so we developed a model, and then we explored what would be the effect of changing different parameters. Is there anything that could help us if we wanted to reduce the non-radiative energy losses? And indeed, there were things that would help. And one of them was to make our charge transfer state brighter. And you could do that in practice if the charge transfer state is then close in energy to the first excited state of the polymer, then you can get some hybridization and the charge transfer state becomes brighter, and then more energy would be lost radiatively, which is good, than non-radiatively, which is bad. So that's one thing. And another thing would be to reduce the reorganization energy, or to change the ratio of charge of basically the amount of interface that you have. So there's some different ideas, and they could then be put forward as recommendations, I guess, to people who are thinking about designing new materials or new devices. So that was kind of the first thing was the first thing I would like to report here is that the non-radiative energy losses in our organic solar cells depend upon the properties, the properties of the molecules, but there are ways in which the molecules could be adapted in order to reduce those losses. And if we look at what has actually been happening recently, indeed, some of these guidelines have been followed. Whether that was deliberate or accidental, I can't tell you. Now that's to do with the voltage. And the next thing I wanted to comment on was the efficiency of charge collection, because that was another way in which our organic solar cells were performing less well. So I'm going to just look for the moment at this sort of cartoon that I've shown before, where we have our heterojunction with a donor and an acceptor. And then whenever we have photovoltaic generation, we come in with a photon, we generate, it'll be absorbed, let's say, in the donor or in the acceptor. In the acceptor, doesn't matter. And then our excited state splits to an electron and hole. We get those at the interface, and then the electron and hole depart from each other, and they give us a charge-separated state. Now, we know from the last study that we would like this to minimize the non-radiative losses. We would like the energy of the charge transfer state to be as high as possible. But if we make it too high, there will no longer be any driving force for this charge separation to occur. And then there's a question about, well, how far can you push it? So if we look at experimental data, this is from a paper that was published, they have looked at photocurrent generation efficiency as a function of the offset. So the thing they're looking at here is a difference in ionization energy between our two molecular materials. And they show that if that difference is too small, you don't get good photocurrent quantum efficiency. But once you get to about 0.4 or 0.5 electron volts, then you're generating current quite efficiently. And we've done similar measurements in our group, where we change the materials, and then we modulate the energetics of the materials. And when we see once our ionization energy gap is big enough, then we start to generate photocurrent efficiently. So that's nice. But if we want to explain that, it's actually not possible to explain it with the model that I've just described, where we're talking about these radiative and non-radiative losses, because that only tells us what happens at open circuit. And now we're interested in what happens actually under operation. So we need to think about what type of model we can use. Now, it's common when you work with molecular materials to have a model where you think about having excited states, charge transfer states, and transitions between them. And these rates of these different transitions, recombination, so on, you could describe with formalisms from physical chemistry quite well. But it's not really useful if you want to describe a device, because in this kind of model of the interface, it tells you nothing about what's happening in the rest of the material. And then if we look at what's commonly done with semiconductor physics, we may have a semiconductor device. We can then model it with some one-dimensional model in which we have equations that describe the generation of charges, the transport of charges, the current and recombination, and we have electrostatics in there. And then we could solve this set of partial differential equations, and we could figure out, okay, this is what current we will get at that illumination, at that voltage, and so on. And that's commonly done with semiconductor physics. But in order to do this, you need to have parameters that will describe the extensive properties of this semiconductor medium. And if all you know is that it's made up of molecules of thiophene or something, you don't really have that information. So there's a kind of problem here, which is that neither model is working very well. One of them is very good for what might be happening at an interface. Another one would be very good for a semiconductor material where you know the parameters. But if you want to find out what material to use, neither of these models will help you. So what you have to do is to try to find a way to bring them together. And this was something we were able to do. We took a semiconductor drift diffusion device model, and then we modified it by introducing the rate equations that describe these different processes that happen at the interface, where you generate an exciton and it may or may not separate, and that charge transfer state may or may not deliver independent electrons and holes. And then the backward processes are possible. It all satisfies detailed balance. So when we put those equations into the formalism for a semiconductor device, then we could describe the entire system. And then we were able to explain for a set of, this is just for an example, a set of material of devices made from different materials that we studied. We were able to explain how the current and voltage and fill factor depended on the type of material, and also as an extra parameter on the intensity of light. And one of the important things here, so in this system, the smallest offset system is the one that's shown in green, and you can see that the system with the small offset was then suffering from a poor fill factor. So poor, it has high voltage, which is good, but poor fill factor because the collection of these charges is poor, and the collection of the charges is poor because once these offsets become small, the back transfer of charges back to the excited state becomes too efficient, and so you don't collect your charges. So that's kind of then understood, and then from a model like this, you could then figure out, if you know your chemical parameters, you could figure out what efficiency you might expect to get. So that would allow us to then make some projections for what might happen. So we take that model, and now we can work out a kind of limiting efficiency for our solar cell, our sort of organic solar cell, as compared to the limiting efficiency for the ideal conceptual solar cell that was studied by Shockley and Queisser. Shockley-Queisser limit is shown here in black, and then a limit that results from our model for the organic solar cell is shown in green. And this is for, so we needed to choose values of a parameters, and in this case we chose a value for the exciton recombination energy of 60 millielectron volts. That's really determining the rate at which this excitonic state would decay to ground, and that would suggest if we could reach that parameter, then in theory we should be able to get to a power conversion efficiency of maybe 25%, and that would be at a somewhat larger bandgap energy than what is normally studied. We can superimpose on this some data representing different reports in the literature. You see that here are some of the super 20% reports, and we see that this sort of the behavior that's expected from the model is reproduced moderately well by reports in the literature, but most attempts to improve the efficiency of our organic solar cells have been focusing on these smaller bandgap materials, and these larger bandgap regimes where there might be some advantage have not been studied very well. But what we can say is that these it's clear that there are some high performance materials out there, and they're performing just about as well as we would expect them to from this model, but there are definitely other opportunities to explore. To make a comment on what has led to these efficiencies, I'm showing here the chemical structures of some of these high performance acceptor materials that have been studied in literature recently, and it's these materials, and particularly this top family here. So this molecule is called Y6. Anybody who works with organic solar cells will know what Y6 is. Anybody who doesn't probably doesn't have a clue. But basically, it's a strongly light absorbing, strongly crystalline molecule, which is absorbing in the near infrared, and it is a component in most of the high performance organic solar cells that have been developed in the last few years. So before I finish, I'm going to just make a couple of comments on what's special about these new materials. So, why, what have they got that's special? I mean, one thing, it's a little bit mundane, but just the fact that, there is quite a variety of materials. So when we put different building blocks together, we can get different properties. And so eventually it's quite likely that something high performance will result. They are, as I briefly mentioned, very ordered. So these molecules, this is Y6. If you look at the molecule from the side, it's completely flat. And because it's completely flat, the molecules are able to stack together like a brickwork and give you something which is quite ordered, quite crystalline. As far as their optical properties go, they have quite long photoluminescence lifetime. So this is showing the photoluminescence lifetime of Y6. So it's got a lifetime of order of magnitude of nanoseconds. And for an organic semiconductor, that's quite high. Obviously, it wouldn't be high in the case of silicon, but for an organic semiconductor, it's pretty good. And these high lifetimes have gone together with long exciton diffusion length. And then a final thing to remark on these, and I certainly don't have time to go further into this today, is that these molecules, once you pack them together, once you take a molecule sort of in isolation and you pack them together in the solid state, you see quite a significant shift in their optical properties. And what that tells us is that when they're packed together, the electronic states are able to delocalize over more molecules. So it becomes less of a kind of a molecular material and more of a kind of a band-like material where the electronic states are able to delocalize. Now, I'm going to finish, I think, with this slide, just to give a kind of summary. So the first thing to say about organic solar cells is that we need a heterojunction, and I think it's still the case that we need a heterojunction to split our excited state into independent charges. Once we have once we have generated this sort of split the exciton, then we have a sort of competition. So if we want to split the exciton and collect charges very efficiently, that will require a large offset at this heterojunction. But when you have a large offset at the heterojunction, then that limits the voltage, the electrochemical potential that you can generate. So there's a kind of trade-off. You can either get high current or high voltage, but you don't usually get them both together. This is a common thing for solar cells. It also applies for ours. Then the dominant pathway for loss pathway is recombination, and that occurs most efficiently through these interfacial states where the electron and hole come together at the interface. And then finally, when we want to extract this charge pair from the interfacial state into an external circuit, the efficiency of that process will then control the overall operational power conversion efficiency and the fill factor. So I'm going to leave it there. I had a couple more slides, which I'm just going to ignore. So these and make some final points. I mean, I think the first and maybe the most important takeaway point is that solar energy conversion is going to be absolutely critical to our future. So if we have in the audience young scientists or engineers or indeed social scientists, this is an area that it makes sense to understand. There's going to be an awful lot more that solar energy conversion can do in the future than it has ever done before, and we're really going to need it. Amongst the different materials that we can use, there are molecular electronic materials, certainly not the only ones, but they're quite an interesting set of materials, and they have some properties that make them interesting, for example, for semi-transparent solar cells, for conformal or lightweight solar cells. If we want to understand them, we need to understand, if you like, both chemistry and physics. Molecular concepts are important in understanding what materials to use, but to see how they work in a device, we also need to understand device physics. So it's quite an interdisciplinary field. And then I could have shown you a bit about how the same materials could be used in solar chemical energy conversion and charge storage, but I sort of ran out of time, so I'm going to spare you that. And I will finish by thanking my co-workers. This is some of my fellow researchers. I would particularly thank the two young men high up on the tree, Mohammed Azuzi and Florin Eisner, and other members of my group who helped to develop the ideas and the experimental work and the theories that I've presented today. And I thank you for your attention. And if there's time, I'm more than happy to answer your questions.
Thank you very much, Professor Nelson, for your nice presentation. So we open the question session. You can either raise your hand and ask directly Professor Nelson. You can write down in the chat and we read them. Or if you are on YouTube, you can write in the chat and also read the question to Professor Nelson. So we start, please. First question. Professor Muñiz, go ahead.
Thank you so much. Do you hear me? Dr. Jenny, do you hear me? Yes, can you hear me?
Not well. Please repeat.
Can you hear me there?
No, I can now hear you well. You might not be able to hear me, but I can hear you.
Yes, I can hear you. I can hear you well, but I don't know if you can hear me.
Perfectly.
Okay, thank you. So many thanks for your presentation. Here the year we have a group that performs quantum chemical calculation. So we're interested. I'm particularly interested in your calculations related to the oscillator strength.
Yeah.
And you said that you also perform calculations for your systems.
Yes.
I'm interested to know which methodology do you use for the estimation of the oscillator strength in your molecular systems.
Yeah.
Do you use time-dependent DFT or something else? Yes, thank you.
So thank you for the question. We use a variety of different methods. It depends on what we want to know, and it depends on the size of the system. So we commonly use time-dependent density functional theory. We are aware that there's quite a significant functional dependence in the results. So when we use different functionals, we are likely to find both different energies and differences in the oscillator strength for the same material. But we're reasonably happy if we're looking at a trend, what conditions will make a state brighter than other conditions. Then we can use density functional theory, and we would repeat it using some different functionals in order to try to make sure that the trend is reliable. When we're looking at a system which is too big to study with density functional theory, then we tend to coarse grain the system and then calculate for a single molecule the transition dipole moment, and then calculate the coupling of these excitonic states to one another using some perturbation methods from perturbation theory to get the coupling, and then calculate for the overall system what the optical properties, for example, what the absorption spectrum may look like. And then we may have some contribution. So the contribution will probably be, depending upon the nature of the state, if it has a lot of Frenkel exciton character in there, then it will tend to be bright. If it has more charge transfer character, then it will tend to be weaker. So we do use these kind of coarse-grained methods. And then we're also using sort of, for very small systems, then we use sort of higher levels of theory, but we tend not to use those a lot because usually the systems that we're interested in are too big for what we can do. So time-dependent density functional theory is the workhorse, but we try to validate the result by, stress testing it with different functionals and different conditions. Is it okay?
Okay, great. Yes, of course, of course. Thank you. Thank you so much.
Yeah.
Thank you. The next question. I have a question about the diffusion model that you used. It's only that would you mind explaining a little further about the physics involved in these equations? Because would you mind? Okay.
Yeah. I will try to do that without taking a lot of time.
Yeah, briefly.
So yeah. So briefly, we have a one-dimensional system, and if we ignore this part, just take the basic drift diffusion equation, then we have a second-order partial differential equation that will describe the generation, transport, and recombination of electrons. Another one that describes the generation, transport, and recombination of holes, and another one that takes care of the electrostatic potential, so it will satisfy Poisson's equation. And then all of these are coupled, and we solve them together using some partial differential equation solver, or you can write your own. I have done that, but nowadays there are plenty of tools you can do. And then we will solve for some space. We would apply some boundary conditions. Usually you have one electrode that is selective for electrons and another one that's selective for holes. And you may or you may not have some permanent charge present in the semiconductor material as a dopant. Normally in our materials, actually, they're not doped, but if you were applying the same tool to a PN junction, then of course you would have to take account of the doping. And then, you know, with your boundary conditions, then you apply the light, you'll have some generation profile within your semiconductor material. You might use a transfer matrix model to solve that if you think interference is important. And then you would change your boundary conditions. Am I in open circuit? Am I in short circuit? Am I in somewhere in between? And then calculate the current and the voltage for these different points along, you know, for these different conditions, and then build up the current voltage curve. And normally it's good practice to do that in the light and the dark. So you calculate the dark current voltage and the light current voltage curve. So that's all fine. Now, what we do, so in such a model, we know it's normally the assumption that if you have a generation rate of electrons and holes, now normally that's identical to the absorption rate of photons in a particular element. So it's some element of space. So as soon as you absorb a photon, you'll assume, if you're in gallium arsenide or silicon, you assume that's the birth of an electron and a hole at that place together, and then they're available to contribute to the current. Now, in our molecular materials, that's not the case, because when your photon is absorbed, you generate an excited state, but it could recombine, and it does that with a reasonable probability. It could separate into this interfacial state, which is not yet an electron and hole, and that state could recombine. And that state could also regenerate the exciton, and then that state could separate. So there are some processes that are not 100% efficient that lead you from generating the excitation in the material to generating the electrons and holes. So the way we deal with it is we introduce these additional rate equations. The first one is telling us that the change in exciton population at a particular point, it's all at a particular point in space, that in any moment of time, you could have generate electrons by absorption, excitons by absorption of photons, and then you could lose them by recombination, or you could lose them by exciton dissociation. And then we have a population of charge transfer states, which are generated from the exciton. They could dissociate, they could separate into charges, etc. And so these are the three kind of rate equations that will take account of what's our population of excitons, what's the population of charge transfer states, what's the population of free charges. And so there are, if you like, some steps that we then quantify that are in between absorbing a photon and generating an electron hole pair. And it's written about in this paper, which is at the link here.
Okay. Thank you very much. So we're going to give time for one last question. So please, if you have one more question, will be welcome.
Yes. Hello, Filiberto.
Go ahead.
Um,
Go ahead,
Thank you very much for the talk. It's a quick question. So now that you understand better your device, where's the room of improvement? It would be in the material or in the device? What is more likely, or what is better to address?
Yeah, I think this is a very good question. So I think there definitely is room for improvement in the materials. But eventually, as the materials get better, then the optimum device would change. And one direction that we seem to be heading in at the moment. So I mentioned as we were going along that with the best materials that are used nowadays, the exciton diffusion length is quite long, the exciton lifetime is quite long. If we then, extend those to the conclusion, that would lead us to conclude that we don't need quite so much heterojunction. You probably still need a heterojunction, but you probably don't need to have this mixture, or not such mixed materials. It's then reasonably likely that the type of devices that would be could in fact be simpler to make or simpler to control would be ones where you have some kind of more or less planar structure, where you'll have maybe some charge separation layer and then your active material. But if we could get to a situation where the exciton diffusion length is long enough, that your active material is able to absorb the light and then generate these excitons that can reach the other side, that would be something that would be advantageous, both from the point of view of voltage and from the point of view of the simplicity of the device. So I think certainly with what's been with publications that have come out recently, we see that things are going in that direction, more towards these kind of planar structures. There's also a great deal of interest in what we call single component solar cells, and I was going to say something about this, and then when I was preparing the lecture, I realized that I don't have time, so I didn't try. But there, there are some reports which will say we can get a photocurrent just from Y6, and you can, but it's very small. But there are other materials where the donor and the acceptor are kind of covalently bonded together, and then they are able to do charge separation intrinsically. However, although those materials are interesting, I'm not sure if certainly the varieties of materials like that are available now, I don't see them. I'm sure that they can solve the problem of generating photocurrent without needing to mix things together. And consequently, they have an advantage in terms of stability, because if they don't need to be mixed together, then there's no risk that they're going to demix, because they're basically chemically tethered together. However, the materials of that nature that are available nowadays are quite complicated to make. And there would be many synthetic steps in kind of making, your donor and then connecting the acceptor. And I'm not sure that that class of materials would really be viable commercially, because they'd be relatively expensive. And my bet would be rather more on finding single materials that had long exciton diffusion length, and then you could prepare a more simple junction structure. So that's my idea. I mean, another thing maybe to comment is that I think there are parts of the parameter space that haven't been explored properly. So I think wider bandgap organic materials could be interesting. They could be interesting for multi-junctions, and that they haven't been explored very much for that yet. And of course, if they were used in multi-junction, that would be a different device structure.
Thank you. If I may just another
Sure.
question.
No problem at all. No problem at all for me.
Just maybe I think I missed it, but what is preventing what is the mechanism preventing from the excitons from moving in the materials? What is breaking them, or?
It's just their lifetime. I mean,
I see.
I guess it's a good question actually. This is not often asked. I mean, so often it will be stated, the exciton diffusion length is typically a few nanometers, and then if the exciton diffusion length then is a few nanometers, it means that if your layer is more than a few nanometers thick, then the excitons will recombine before they can get to the other side and break up. And now we have materials where the exciton diffusion length is up to 30, 40 nanometers, and maybe that can increase. And the reason why the exciton diffusion length is increasing, I think, is due to a number of things. One is that with these molecules that are very flat and can be packed together in an ordered manner, we have spreading out of the wave function over multiple molecules. So your exciton basically becomes bigger, and if it becomes bigger, it can move further. Yeah.
But are these Frenkel excitons or
Mott-Vanier excitons? I would say they're big Frenkel excitons.
They're big Frenkel excitons. Okay.
I can't call them Mott-Vanier excitons unless I've got a band structure, and I don't think I do.
Right.
But they're not localized. So we think of them as being localized on single molecules, but I was showing this down here where we compare, this is the absorption of Y6 alone or in a film, and this is a big redshift. And it's clear that whatever the exciton is in the film is not the same as what the exciton is in the molecule. They've spread out. So I don't know what you want to call them.
Right.
But I would say they're probably something in between. They're certainly not the Frenkel exciton as we traditionally think of it as being localized on a single molecule, but something which is delocalized. And when we do the calculation of the electronic structure of this sort of mini crystal, we do see that our states are delocalized over many molecules, over several molecules.
Right. I'm sorry, I interrupted you. You were saying about the why they don't diffuse.
So I'd say so I guess I was giving the reasons why I think they do diffuse when you have materials like this. I'd say because of delocalization and because the amount of disorder is relatively low. In traditional materials, when you have more disorder, then it's more likely, disorder in the site energies for the excitons, they're more likely to get stuck. And if the exciton is strongly localized, so not delocalized, then it will find it harder to move. You always have a polaron or exciton binding energy or whatever. Some activation is needed to move to the next site, The more delocalized it is, the easier it'll move, the less disordered it is, the less likely it is to get trapped. So I would say, I think the reasons why the exciton diffusion length was short would be to do with, so first of all, simply the exciton binding energy, which kind of goes along with localization, and also disorder in site energies that tends to encourage the excitons to find the lowest energy place and stay there.
Okay. Thank you. It's very interesting.
Yeah. Thank you.
Thank you very much.
Thank you very much. Well, with this, we finished the seminar for today. So, Professor Jenny Nelson, thank you very much for being with us. It was an interesting talk. And thank you all for your attention.